For 10.2, we will begin talking about what we call the law of sines and the law of cosines. And what these two laws are ways to relate angles and sides of a triangle that are not right. So if you think about sine, cosine, tangent, secant, cosecant, cotangent, most of what we've discussed about those in terms of triangles has been in relation to a right triangle. So opposite over hypotenuse, adjacent over opposite. So we're relating side lengths and angles, but those have basically been restricted to right triangles for the most part. So the law of sines is a law that relates the sine of an angle and its opposite side to the sine of another angle in a triangle and its opposite side. What that means in general is, if you look at this triangle drawn over here, if we look at angle A and side A, they are opposite of each other, and C and angle C are opposite of each other, and B and angle B are opposite of each other. So the law of sines basically says that if I take the ratio of the sine of an angle and its opposite side, it's equal to the ratio of sine of another angle in the triangle and its opposite side. And that's true for all of the angles and sides in any triangle. And then another way I could rewrite it is A over sine of A, B over sine of B, or C over sine of C. So what we'll be using this for is a way to find other pieces of information about a triangle dependent on what we're given. So in terms of a proof, it's actually a fairly straightforward proof. If I write the area of that triangle shown using the area formula we talked about the other day, here's what I would have. So let's say I looked at the area of that triangle using angle A. So if I look at angle A and I have B and C, which are the sides that make up angle A, the area of this triangle would be 1/2 BC sine of A. Now, I'm in the same triangle, so I could express the area using a different angle. So if I look at angle C, the area would be 1/2 AB sine of C. Those are A and B are the sides that make up angle C. And that should also be equal to 1/2 AC sine of B. So all these areas should be the same because they're all the same triangle. And we proved the area formula the other day, so this shouldn't be that surprising. Now, in terms of rewriting this so that it looks like our law of sines, if I multiplied through this equation by 2 over ABC, here's what would happen. So if I do 2 over ABC times those three areas that I've set up that should be equal, here's what would happen. So in the first one, the 1/2 BC sine of A, the 2 and the 1/2 would become 1, and then the BC would reduce with the BC in the bottom, and what I'd be left with is sine of A over A. And then if I multiply 2 over ABC through the second one, I should get sine of C over C, and through the third area should be sine of B over B. And essentially what that says is if all the areas are true, and I just do legal algebra, to multiply by 2 over ABC, multiply everything since it's an equation, I get the law of sines. So again, it's just a way that we can relate angles and its opposite side in a way that we can find some missing information. So let's look at a straightforward example. So if we look here, find the length of x in the triangle shown. So x is the side opposite the 135-degree angle, and 20 is the side opposite the 30-degree angle. So again, we're looking for the length of x, and again, it's not a right triangle. We don't have the other side, so it's not like I could use the Pythagorean theorem or any of that. So what I could do is set up a proportion, essentially, or two fractions equal to each other. So sine of 135 over x should be equal to sine of 30 over 20. Or I could write it x over sine of 135 equals 20 over sine of 30. Those are both equivalent. I'm going to work with the one on the left because it's typically how you'll see it, but you should be able to find the same solution either way. So now in order to solve that, I would get 20 sine of 135 is equal to x sine of 30. And what I multiplied by 20x, both sides, which is essentially clears fractions. You might cross multiply to solve that. And then divide both sides by sine of 30 to get x by itself. So x should be 20 sine of 135 over sine of 30. That would be an exact answer. The only difference here is sine of 135 and sine of 30 are things that we know. If they were angles that we didn't know how to evaluate, we could leave it like that in terms of finding an exact value or use our calculator. So I'm going to evaluate. I know sine of 135 is root 2 over 2, and sine of 30 is 1/2. So I have 20 times root 2 over a half, which simplifies to 20 root 2. So the length of x in the triangle shown is 20 root 2 centimeters. If you look at example 2 here, we want to find the length of y in the triangle shown. I'm going to draw some arrows here, at least at the beginning, just so we can get used to how we're going to apply this law of sines. So y is the side opposite of theta. 10.2 is the side opposite of 75. Notice I'm not going to use the 62-degree angle in this case because I don't know the length of the side opposite. So I'm just going to use the angles and sides that I've drawn arrows between. Now the difference here between the problem before is I don't know what angle theta is, but because 3 angles in a triangle add up to 180, I can find it, and I should get 43 degrees for that angle. So then if I want to set up a proportion or two fractions equal to each other using the law of sines, here's what I would do. So I'd say sine of 75 over 10.2 is equal to sine of 43 over y. Again, please make sure that the angle that you are putting over your side, it's the ones that are opposite each other. People have a tendency sometimes to write the side adjacent and the angle, so please be careful there. So then in terms of simplifying that, I'd multiply both sides by 10.2y, or clear fractions, or cross multiply, whatever algebraic technique you want to use there. So I have sine of 75 equals 10.2 sine of 43. Just right here, you should know that you're going to have to use a calculator because sine of 75 is not an angle we know, sine of 43 is not an angle we know, and we're going to multiply it by a decimal value anyway. So I'd solve for y, and then to find out what that value is, I would use my calculator. Please make sure your calculator is in degree mode when we're dealing with degrees. So then what I should get for my value for y is 7.202 inches. And again, we want to round that to whatever is specified in the problem, and if nothing's specified, we want to go to 3 decimal places. So for our next example, we want to use the law of sines to solve a triangle. So what that means to solve a triangle is basically find all the missing information. So if you look at the triangle here, we have 8 feet as one side length, 4 root 2 feet as another side length, and we have an angle of 45 degrees, which is not in between my two sides. So if you think back to geometry, this would be what we call an SSA triangle in terms of this information that we're given. 2 sides and an angle that's not in between them. So the information that I'd be looking for, what I need to find is the measure of angle B, the measure of angle A, and the length of side A. So the first thing I'm going to do is find the measure of angle B. So notice when I set up my law of sines here, I did sine of 45 over 8, which is 45 and 8 feet is opposite of it, equals sine of B over 4 root 2. And just looking at that, the only variable in there is B, and that's the angle that we're going to be looking for. So in terms of solving this, I'd clear fractions, multiply both sides by 32 root 2, or cross multiply. And then to finish this, I'd get 4 root 2 sine of 45 equals 8 sine of B. So then I have 4 root 2, and I'm going to evaluate sine of 45, which is root 2 over 2. And then if I multiply everything on the left side, I would get 4 root 2 times 2 root 2 over 2 is 4. And then dividing both sides by 8, basically getting sine of B all by itself, what you should get is 1/2 equals sine of B. And then right here, I do want to just pause for a second and talk about what could happen. So in law of sines, there's some things we have to consider in terms of an angle. Now, the triangle is drawn for us, so you can kind of see, or at least looking at the angle B, you kind of have an idea of what the measure might be. You know, it looks like an acute angle. But if I had the same information given to me and didn't have a picture, there's something to consider in terms of how to find some missing information. What I mean by that is sine of B is 1/2. There's really 2 angles where that's true, 2 angles between 0 and 180. Reason why it can't be more than 180 is because that'd be more than the sum of the angles of a triangle. Can't be 0 because then you wouldn't have a triangle. So the two angles that work for B are 30 degrees or 150 degrees. So since that's 1/2, it's not like I didn't put that in my calculator. I just know that those two angles give me a sine equal to 1/2. And thinking about what angle works here, we'll talk a little bit more about some special cases of the law of sines, but for right now, just think about the possibility of those two angles. Does 150 degrees make sense? So if I put 150 degrees in for B, now thinking there wasn't a picture, 150 there plus 45, which is the angle that was given, is already bigger than 180, which means there wouldn't have enough angle left to draw a third angle, because 150 plus 45 is 195. That's already bigger than 180, which means I can't construct a triangle where angle B is 150. So essentially what I'm going to do with that information is cross out 150. We'll park down in the special cases or some restrictions about our angles a little bit more on Monday, but the idea is there are technically two answers, and your calculator could give you one and not the other, and we have to consider both answers if it's reasonable for a triangle. But for now, angle B is 30 because that's the only one that makes sense because of my given angle. Now, I'm going to put that in there, knowing 30 degrees. Now, there's two ways to go about finding angle A. You could either set up a law of sines for it, but if I have three angles in a triangle, they add up to 180, I'm just going to find the third angle by using that fact. So 180 minus 45 minus 30 means angle A is 105 degrees. So I found my two angles. So I have all three angles, and I need to find my third side. I needed to find angle A so that I can find side A using the law of sines. So my setup would be sine of 105 degrees over A is equal to, and then you could pick which angle and which side you want to use. I'm going to use the two given sides and angles, or 45 degrees and 8 feet. You could use 30 degrees and 4 root 2 feet. That works too. But I'm just going to use those. So solving for A, I would get A sine of 45 equals 8 sine of 105. Divide both sides by sine of 45. So now here I'm going to do a little bit of algebra. I would multiply the top and bottom by 2, essentially clear fractions in the bottom. So I have 16 sine of 105 over root 2. And then you could plug this in your calculator and get a value. I'm just going to go a little bit further. I'm going to rationalize this because it works out to be something that's a little bit cleaner looking. So I get 8 root 2 sine of 105. That would be my exact answer for the length of side A. And then if I wanted a decimal approximation, I would put that in my calculator, and I would get 10.928 feet. And the last example we're going to take a look at here, we are going to use this figure that's given, the information in it, to find the distance from P to R. So if I take a look at the information that's given, I'm going to start here in my little triangle, because in order for me to find the distance from P to R, I would need to find the length of PQ and the length of QR and add them together. So to find the length of PQ, I'm actually not going to use the law of sines for that. I'm just going to use the trig functions we've been using before. So tangent of 24 would be the opposite side, which is 1, over the adjacent side, which is PQ. So then I want to kind of rewrite that as an expression for PQ, which would be 1 over 24 degrees. I'm going to leave it like that for now because I don't want to get a decimal answer for that and then use a rounded answer in the rest of my calculation. So I'm just going to leave PQ like that for now. I'm going to shift over to the other triangle. Now notice this bigger triangle is not right, which means I'm not going to go tangent or cosine or sine using like a hypotenuse and a side length. I'm actually going to have to use the law of sines here. So I know right away that angle is 108 degrees, the missing angle, because all of them have to add up to 180. So once I know 108, which is the angle across from QR, I'm going to set up a law of sines for that triangle. So sine of 24 degrees over 2 should be equal to sine of 108 over my missing side, which is QR. So then I want to solve for QR, get that by itself. So one thing that I'm going to do here, and it's probably not a very common algebra step, what I did was you could cross multiply, set them equal, But if two fractions are equal to each other, that means their reciprocals are also equal to each other. So I just flipped both fractions. Again, that might not be something that's super comfortable for you, but the reason I did that is because now the quantity I'm trying to get by itself, QR, is no longer in the denominator, which means if I multiply both sides by sine of 108, then I would have QR isolated. So that is an expression for QR. It's not going to be a nice number because 108 and 24 are both angles that we don't know exact values for. So now if I want to use that information that I've found for PQ and QR to find the total length from P to R, I would just add them together. So PR is going to be PQ plus QR. So that's 1 over tangent of 24 plus 2 sine of 108 over sine of 24. And then to find an actual decimal answer for that, I would put those in my calculator, making sure that my calculator's in degree mode, and I would get 6.923. Now, there's no unit in the problem. It's not like they said 1 inch or 1 foot or 1 mile. So it's really not a unit I can attach to that answer. You could put units if you'd like, but I'm just going to call it 6.923. Again, I'm going to go to 3 decimal places unless otherwise specified. So these are a few examples on how to apply the law of sines. Practice these for your homework for day 3, and then we will talk about the law of cosines next time.